the workshop, I guess. The next speaker is Mike Flynn. I think all of us know who Mike Flynn is. I mean, his work, the MIMD, SIMD, that categorization, that's his taxonomy, which we all know and love. He was a professor for many years at Stanford. He's retired now, and he's working at Maxillr. Mike?
Okay. Well, good afternoon. And I'm not a student of Yale Patt. Not only that, I'm even older than Yale Patt, which is hard to believe, I know. And in fact, I'm going to tell you in my first part of my talk what I was doing when Yale was in high school. Okay? And it's hard to believe. It's hard to believe all of this, but I want to talk about, you know, your first machine you work on is like your first love. You always go back and think sort of fondly about this, you know, whether or not a lot of water is passed over the bridge or under the bridge by that time, but there you go. So now, the machine itself that I'm going to talk about wasn't particularly interesting. I mean, it's, well, it's so familiar, although it was its earliest version. The instruction set was touched by von Neumann, to go back a few slides. And I want to go to the automation, but the thing that impressed me most when I was a young engineer with in this project was a system that IBM was introducing at the time to automate design and manufacturing. I'm going to tell you about it because it resembles some of the things we're doing today, but now that, of course, similarity probably is colored a great deal by my experience with my first love here. So, but I'll tell you about it because it still was an interesting moment in the evolution of machine design. Now, I can't stop this thing from advancing. What do? I'll go back. There we go. So, no. Yeah, okay. Now, and it represented the, what I would call the dawn of design automation. This was the first truly integrated system which put it all together. There used to be things like this. This was the earlier generation before the transistor came along. I can't stop this damn thing from advancing. What is there, some ghost here? Or they want to hurry me along in the talk. so you can see this is all hand done. And what transistors had been, were now in production. We have to.
So tell you what, you talk, I'll try to figure it out.
Okay, fair enough.
All right.
Transistors had been developed, and an automatic insertion of cards had been developed, a component insertion. Wave soldering was there, so we could automate the production of cards. And, okay, yeah, okay. Not only that, the goal would be to do something bolder than that, to bring together the designer. So once the designer had done something, it would go right into production without having any other human intervention. The machine would do it, okay? So this was the SMS, Standard Modular System. And it was developed in '56. It lasted for 5 years, and IBM threw it out then and went on to something bigger and grander. The cards were standardized, about like 20 cards, what we would think of as ECL cards, with current switching in the days. Automatic wire wrap back panel and standard frames. 4 6-foot pages, 4 panels a page, 240 cards per panel. And they span from small machines to big machines. So the key to it from the designer's point of view was something called the ALD, Automatic Logic Diagram. The designer could simply, this would be a sheet, perhaps 18 inches by 24 inches, would have maybe about 36 of these little boxes. And the designer could simply put a logic function in there, or it could specify something more, the actual card type, and he could also specify the socket number. But he didn't have to. If he just put down the logic function, the system, and also drew the connection to another block, the system would figure out what type card was required and what socket it would assign it to. So now, the card looks something like this. It was reconfigurable to a degree. You can see something in the middle called a cap. You could cut those caps to get dot ORing or other functions. So this reduced the number of cards that had to be made. Cards fit into the sockets, and 4 of these molded sockets would form a row, and 10 rows would form a panel. And you could see the pins, square pins coming out at the right side to be wire wrapped. Now, the amazing thing about this was the design automation system. As I say, it assigned card type to logic, assigned card to a socket, designated pins for wire connection, and did a wire wrap routing system, like a place and route, effectively, when it was all done. And it did some limited logic simulation, and it would print out the ALD again, as it had updated it, and this was done with a line printer. That's why these little boxes are all square, so you could do this with the printing technology of the day. When it's all completed, the system would produce a card deck to drive this Gardner-Denver machine. These are these pooled-sized table machines which would wire these panels in an amazing system of arms moving around, pneumatic sounds coming out this way and that way, and you could wire a panel in less than an hour. About 4,000 or 5,000 wires. And use a bed of nail testing to validate, again, with the same card deck. So, from the designer to the machine, at least to the panel level, it was automated. Finally, we had the possibility of doing automated design and building really nice machines in just a few days rather than a few months. Now, this is the 7090. I guess Yale had just graduated college now, or coming into college. Okay, so there he is. Okay. In any event, as I say, it was done in days. The costs were much reduced, but IBM, surprisingly enough, didn't reduce the customer cost. So it still kept it up there. These babies would, each frame were rented, and as I understood, for 1 month's rent, that would recover the manufacturing cost. So, today, at least in my view, we want to automate programming for maximum speed up. And we're going to emulate the production line. This is our work at Maxeller. And in doing this, I prefer the most restrictive kind of parallelism and then less restrictive. It's not just simply enough to get parallelism. It's the kind of parallelism that you get that's very valuable. I don't want parallelism where things have to go through locks and gates and whatever else and sit around idly. I want to have a lockstep parallelism insofar as we can achieve it. I want to do that first before I go on to these less restrictive forms of parallelism. So we're going to support parallelism, multi-core for control flow and data flow for compute-intensive kernels. And we're going to use a 2D, spatial programming to implement the data flow. So now this is the way our system is laid out from 10 yards away. We're going to use FPGA accelerators. The FPGA is going to emulate the data flow, and we're going to take a standard server, a high-end server, and we're going to use a PCI Express card with an FPGA on it, which represents the data flow of the compute-intensive portion of the application. We're going to split the application in two, and what we can put on the FPGA, that's that data flow, which is the compute-intensive portion. We're going to do that, and we're going to where you can use up to 4 of these cards in one server box. So we're going to, again, with this notion of keeping the lights on, no dark silicon, static synchronous streaming data flow machines. Unroll the loops. We have a version which is latency, which optimizes latency, but I won't talk about that in these few minutes. I'm going to talk about compute-intensive applications. Fully synchronous data flow machine, synchronized to multiple memory channels. The time through the data flow machine is always the same because it's static. And we're going to stream computations along this long data flow pipelined array. And we're trying to use all of the pin bandwidth of the FPGA and all of the silicon area, and insofar as we possibly can, to maximize the speed up. So, this is a graphic of what I just said. We have data comes in from the host memory. Remember now, the computation already has been written for the host. We take out the compute-intensive portion, put it in a data flow machine, put that in the FPGA, and then create this long data flow machine pipeline. This pipeline is frequently 3,000 or 4,000 stages deep. And buffer the intermediate results. Now this is key. The intermediate results, many applications are memory limited. So the goal here is to take just the source data from the host memory, keep all of the intermediate results on the accelerator card, and write the final results back out to host memory. That's the goal. We have 48 gigabytes of memory on a card now, and I think in a few months we'll be going to 96. So there's a lot of intermediate memory, and it's that intermediate memory that helps us avoid memory bottlenecks. We have a graphic programming language and interface. We could write a language, some statements like this on your your left, and the compiler produces the graphics. And naturally, the compiler also handles streams and offsets within the streams so that you could handle computations like this, and the graphic and the compiler produces the graphics. And for choices, we have a mux to make the selection for among paths as they go through the computation. So it's all static. Now this is an actual graph of an application. Now, I should spend a little time on this. The application, the computationally intensive portion of the application is written in whatever. One of our folks takes this and creates from this a data flow machine. The programming paradigm is data flow, and the syntax is Java. And in doing this, every one of these dots represents an operation. So it looks at all the operations and reconsiders the parallelism available, the algorithm that's being used, and the data structures, and puts it all, and then changes the aspect ratio. This is now showing all of the parallelism that's available in the program at this point, but it won't fit exactly this way on an FPGA, so you have to modify it to make it fit. So, as with SMS, it's the software that counts. Compiler provides the graphic interface, ALD-like. Nodes are grouped by the designer interactions, and the compiler organizes data flow streams and memory choreography. This is very important because we have a static flow of a pipeline, so the memory, we have 6 channels of memory, and they have to provide new data every single cycle to all the pins. There's no such thing as having a miss or something. It has to provide new data every cycle. And the compiler provides area and timing information. And you can do a cycle-accurate simulation of the design, so the design performance is known at the end of the iteration of the design study. And when the design is complete, you do the place and route as you did with the old SMS system. So this is what the system looks like hardware-wise. And now, the performance is excellent, but this is sort of like a Rolls-Royce, because these data flow cards are not cheap. Each one costs more than the, let's say, the Intel Xeon cores. So you have to really want the performance to make this whole thing work out. You're putting a lot of effort into it, you're changing things around, but if you need the performance, this is the way to get it. And we typically see taking the box without the cards and the box with the cards for most applications that we look at, and that's largely in banking and in oil and gas with people with money. We see speed-ups of 20 to 40 times. That's not cost performance now, that's just raw performance based upon the cards, the 4 cards. So that you can, as far as the 2D programming model is available, you can access it, and it's available to anyone that wants to, and you can see what we offer with it, and it's, as I say, it's available for anyone that wants to look at it or consider it, and there's no cost. So now, here's the question that came to me initially. We're only emulating this stupid data flow machine. Imagine if the data flow machine was really there. We could have really significant, if we're getting 20 to 40 times now, what could we get without an emulation? Emulation is known to be 2 or 3 orders of magnitude poorer than the dedicated machine. Well, that's a little misleading, because many of these FPGAs have 2,000 or 3,000, or 1 to 2,000 multipliers, and we use every single multiplier. That forms the basis of our data flow machine. So, but it still says that there's there's some orders of magnitude available if we could really find an effective dedicated data flow chip. Now, I want to reflect on all this and go back to the great debate of 1967. Amdahl versus Slotnick. And Amdahl, of course, says you have to go sequential model. It's a madness to do anything else. It takes too much time to program. It takes too much time to do this, that, and the other. IBM's always going to give you a better machine. It's a qualitative version of Moore's law of frequency scaling. So Slotnick, the real pioneer of parallel processing, and if you don't know him, I'm sorry about that, but he's the developer of the ILIAC 4, and a great man who died quite early in his life in the 80s, and but certainly one of the great figures of the computer architecture. And in essence, he says, you got to rethink everything: numerical analysis, data management, data types. And in essence, he's saying parallel processing is achieved by programming effort, education, and tools. Okay. Now, it occurred to me, looking back on that we teach students computational complexity a little bit. So which is better? An algorithm that does n log n or n squared? Well, we're taught it's n log n. Wrong. Because frequently when we see this in our data flow, we take out, let's say, FFT, which is n log n, and put in convolution, which is n squared, because there's more parallelism. You see, our notions have been molded already by this victory of Amdahl in 1967. And of course, he was right. Amdahl was right for 40 years, but something happened about a decade ago which changes things. Also, the kind of data structure, the kernel that you use to, not the kernel, the template that you used in a sparse matrix to evaluate to order the points is different for a parallel processor than it would be for or the stencil, I guess it's called, is different from a parallel processor than it would be for a 5-point stencil for a single processor. So, and finally, the advantage of seeing, you can't see what's happening. Well, that's why I claim that we need some sort of a graphic interface. Maybe it should be 3D interface to see what's happening in the execution of a parallel program, so you understand what we have to fix and how to fix it. So, speed up is achieved by these things. Now, my final comment is that, remember, SMS, I was talking about earlier, starts out with a clean slate, a clean sheet, right? Nobody was doing anything like this before. So the designers of this system could do anything they wanted to. We now, in moving from computing to a parallel platform, don't have a clean sheet. We have sort of 40 years of dirty sheets that we have to launder in some ways, algorithmically. The mathematics, the way we train people. I won't even talk about the religious aspects of programming languages. But all of these things have to be rethought in order to have an effective future. Lots more work to be done, but we'll all learn about this at Yale 85. Thanks.